So we're going to be reading chapter 16, Extended Attributes. Let's take a look at this chapter. Overview, extended attribute implementation details, system calls for manipulating extended attributes. It's an example program, and that's it. It's a very small chapter, really. Should be able to blast through this. It's just, let's see, 311 to 318, so 7 pages. And one exercise at the end. So, not a lot here. I had planned to just do this until 4:30, which should be 3 hours here. But I'm guessing I'm gonna get into, I didn't realize it's such a small chapter, but I'm guessing I'm gonna get into the ACLs. So we'll add start reading ACLs. Alright. Cool. So far we have the traditional attributes that are part of the file system, things like permission bits, sticky, set UID, set GID, timestamps, stuff like that. Let me turn off this music. Boop. So yeah, we have the traditional file attributes, file type. I'm trying to think what else. I think that's about it. In my mind, there's like this bit, series of bits. So you have the 9 bits for the permissions, for the 3 permissions for 3 groups, read, write, execute for user, group, and everyone. So that's 9 bits. And they have an extra 3 set of bits, which are set UID, set GID, and sticky. And then you have an extra 4 bits on the end there, which are the bits for the file type. And those are all the attributes. And then, of course, the timestamps. Let's see. Let's talk with AI real quick here. Can you list the traditional file attributes in the Unix system? In Linux. I don't care about Unix. My mental model has a set of 9 bits for permissions and extra 3 bits for SUID, SGID, and sticky, and then a final 4 bits for the file type. This might constitute a file mask, if that is the right term. If not, let me know. Additionally, there are timestamps, things like access time, modified time, birth time. What was the other one? Access modified. So data access. What are the timestamps? I know there's 3 outside of the. Well, they should be in this chapter previous here. Permissions. Oh, the actual owner group. The owner and group of the file. Okay. C time, which is not creation time. Last file access, last file modification, and last file status change. So it'd be inode modified. What else? Sorry, it's called mode, not mask. File mode. The device ID. Number of links. Is there any other important information considered as file attributes other than these? Also, where is all this information stored? Is it on the inode? File mode encodes 3 things. File type 4 bits, sometimes more. Additional permission bits, special permission bits. So let's run on that. Timestamps. And of course B time. Ownership, links, device Ds. File size. We didn't talk about any of those. We'll talk about those later. Everything above, mode, UID, GID, endlink, timestamp, size, RDEF, inode number is stored in the inode. The inode itself is part of the file system metadata, separate from the file's data blocks. Extended attributes are usually stored in the inode if small enough, or in special blocks associated with inode. So yes, your intuition is right. The inode is central storage. Okay. I don't want a diagram. So there's all that traditional stuff, which is like the file attributes, which is stuff that's stored in the inode. And then there's these things known as inode extended attributes, or inode attributes, or inode flags, which are things like, oh, this file is immutable, it's an append only, secure deletion, things like that. Those are more implemented by the file system, but they're stored on the inode, so they call them inode flags, or sometimes file extended attributes. And then there's what we're going to be talking about now, which is extended attributes, which I think is stored, like it's like arbitrary data that you can store on the file. I think it's like not constrained to a set of like bits of data that you can like store data in. It's like arbitrary storage of arbitrary attributes, but we'll see. That's my expectation going into this, is that kind of like in Kubernetes, you have like what do you call it, metadata as attributes. My Kubernetes brain is atrophying. Yeah, attributes. Is it attributes? Oops. It's metadata attributes. Yeah. We'll just search for metadata. Yeah, the labels, which are like things that are queryable from the API. Then you have you took all attributes, right? Annotations. Sorry. My brain is just like fried with all this attribute stuff. Annotations. The annotations are arbitrary key value. So I think these attributes are going to be something similar, hopefully. That's my expectation. This chapter describes extended attributes EA, which allow arbitrary metadata in the form of name value pairs to be associated with file inodes. So yeah, kind of like Kubernetes annotations. EAs were added to Linux in version 2.6. Overview. EAs are used to implement access control lists, chapter 17, and file capabilities, chapter 39. Interesting. However, the design of EAs is general enough to allow them to be used for other purposes as well. For example, EAs could be used to record a file version number, information about the MIME type, or character set of the file, or a pointer to a graphical icon. EAs are not specified in SUS v3, however, a similar feature is provided on a few other Unix implementations, notably modern BSDs, extended adders, and SOLIS 9CF adders. EAs require support from the underlying file system. This support is provided in BTRFS, EX2, 3, 4, JFS, RiserFS, XFS. Support for EAs is optional for each file system and is controlled by kernel configuration under the file systems menu. EAs are supported on Riser since blah, blah. This book talks a lot about Riser, given that it's like no longer in the kernel source. I feel like it's one of the glaring, like, dated aspects of this book. That and EXT2. Anyways, EA namespaces. EAs have names in the form of namespace names, so similar to Kubernetes annotations, which usually have like kind of like a domain type namespace. Form of namespace.name. The namespace component serves to separate EAs into functionally distinct classes. The name component uniquely identifies an EA within the given namespace. 4 values are supported for namespace: user, trusted, system, and security. These 4 types of EAs are as follows. User EAs may be manipulated by unprivileged processes subject to file permission checks. To retrieve the value of a user EA requires read permission on the file. To change the value of a user EA requires write permission. The lack of the required permission results in e-access error. In order to associate user EAs with file on for the file system, an underlying file system must be mounted with the user xadder option. Let's see if we have any of those mounted. Mount grep xadder. I do not. Let's just grep for adder. No. Hopefully it's a default in some of them. Trusted EAs are like user EAs in that they can be manipulated by user processes. Difference is that the process must be privileged, capsysadmin, in order to manipulate trusted EAs. System EAs are used by the kernel to associate system objects with a file. Concurrently, the only supported object type is an access control list. Security EAs are used to store file security labels for operating system security modules and to associate capabilities with executable files. Security EAs were initially devised to support security enhanced Linux, SE Linux. NSA.gov/research/SE Linux. An inode may have multiple associated EAs in the same namespace or in different namespaces. The EA names within each namespace are distinct sets in the user and trusted namespaces. EA names can be arbitrary strings. In the system namespace, only names explicitly permitted by the kernel, e.g. those used for access control lists, are allowed. JFS supports another namespace, OS2. that is not implemented in other file systems. The OS2 namespace is provided to support legacy OS2 file system EAs. A process doesn't need to be privileged in order to create OS2 EAs. Creating and viewing EAs from the shell. From the shell, we can use the set f adder and get f adder. So the same analogous stuff for the inode flags were ls adder and ch adder. So these are set and get f adder. So ls-la, if we just like get f adder of readme, can we set f adder name and path, name, value, and path. Let's do that. So we set f adder name foo path or value bar on readme sudo bang bang. Man set f adder. So it's set f adder name value path name. A new value with extended attribute name for each specified name. Value. Okay. So why is it complaining here? Maybe because the file system doesn't support it. Well, let's continue reading. So we touch a file, we set adder user.x. Let's try that. User.foo. Hey! And then it's ls adder or get adder. User.foo readme. Get f adder, sorry. Yep. And then if I do, I'm just gonna set adder dash x. Man set f adder. I think it was dash x, right? To delete it. X name remove. Oh, it's x name. Like that. There we go. And then if we get adder, it's like, hey, I don't have anything. Can I set it again here? Without sudo, yeah. If I get adder everything on readme. Okay, it gives me back all the names, and they can look them up individually. Okay. So we set f adder user x y. Dump all values of EAs dash D. So I have to do dash D here, dump. Set f adder okay. One of the points that, oops, sorry, went to the next page here. One of the points that the preceding shell session demonstrates is that the value of an EA may be an empty string, which is not the same as an EA that is undefined. At the end of the shell session, the value of user X is an empty string and user Y is undefined. Because deleted user Y. By default, getAttr lists only the values of user EAs. The -m option can be used to specify a regular expression pattern that selects the EA names that are to be displayed. The default value for pattern is user. We can list all EAs on a file using the following command: getAttr m-file. GetFattr m-readme. Yeah. Extended attribute implementation details. Oh, did I mess up the thing here? Yeah, my paging was off. Okay, extended attribute implementation details. In this section, we extend the overview of the preceding section to fill in a few details on the implementation of EAs. Restrictions on user extended attributes. It is only possible to place user extended attributes on regular files and directories. Other file types are excluded for the following reason. For a symbolic link, all permissions are enabled for all users, and these permissions can't be changed. Symbolic link permissions have no meaning on Linux, as detailed in section 18.2. This means that permissions can't be used to prevent arbitrary users from placing user EAs on a symbolic link. The resolution of this problem is to prevent all users from creating user EAs on symbolic link. For device files, sockets, and FIFOs, the permissions control. There's some more light in here. For device file sockets and FIFOs, the permissions control the access that users are granted for the purpose of performing I/O on the underlying object. Manipulating these permissions to control the creation of user EAs would conflict with this purpose. Furthermore, it's not possible for an unprivileged process to place a user EA on a directory owned by another user if the sticky bit It's not possible for an unprivileged process to place a user EA on a directory owned by another user if the sticky bit is set on the directory. It's fine. This prevents arbitrary users from attaching EAs to directories such as temp, which are publicly writable, and so would allow arbitrary users to manipulate EAs on the directory, but which have the sticky bit set to prevent users from deleting files owned by other users in the directory. Implementation limits. Linux BFS imposes the following limits on EAs and all file systems. The length of EA name is limited to 250 characters, and EA value is limited to 64 kilobytes. I mean, this is very similar to Kubernetes annotations. In addition, some file systems impose more restrictive limits on the size and number of EAs that can be associated with a file. On ext2, 3, and 4, total bytes used by the names and values of all EAs on the file is limited to the size of a single logical block, 1024, 2448, or 4096. Alright, system calls for manipulated extended attributes. In this section, we look at the system calls used to update, retrieve, and remove EAs, creating and modifying EAs. The setxattr, lsetxattr, and fsetxattr system calls set the value of one of the file's EAs. So setxattr, you give it a path name, the name of the attribute, the value of the attribute, the size of the whole thing, the combination of both. That does make sense. Maybe the size of the value because it's a const void, which potentially could not be null terminated. I don't know. I don't know what that size is, which one that applies to. It's probably value. And then in flags, lsetxattr is the same prototype. I would think that one wouldn't follow symbolic links if it was the same pattern as we've seen in the past, But given that you can't set extended attributes on symbolic links, then what would be the point of that syscall? I'm not sure. fsetxaddr is just the same, but has a file descriptor as its first argument. The difference between these three calls are analogous to those between stat, lstat, and fstat. Setxaddr identifies the file by path name and dereferences the file name if it is a symbolic link. Identifies the file name by path name, but doesn't dereference symbolic links. Okay, it doesn't matter the dereferencing stuff. Okay. I guess that might be useful in some situation. The same distinction applies to other groups of systems calls described in the remainder of this section. Boop. The name argument is a null terminated string that defines the name of the EA. The value argument is a pointer to a buffer that defines a new value for the EA. The size argument specifies the length of this buffer. By default, the system call create a new EA if one with the given name doesn't already exist, or replace the value of an EA if it does already exist. The flags argument provides user final control of his behavior. It may be specified as 0 to obtain the default behavior, or as one of the following constants: xaddr create, xaddr replace. Here's an example using setxaddr to create a user EA. So we declare a char star for value. We then assign it in to the literal. The pass is not dead. And then we say, hey, we're going to set the xaddr on this path name, which is not defined. We're going to say user.x, the value, and then we'll give it a stir line of the value, and then no flags, and then we test the error. Retrieving the value of an EA, get xaddr, L get xaddr, F get xaddr, look all the same, except you provide it place to write into. The name argument is a null terminated string that identifies EA whose value we want to retrieve. The EA value is returned in the buffer pointed to by value. This buffer must be allocated by the caller, and its length must be specified in size. On success, these system calls return the number of bytes copied into value. If the file doesn't have an attribute with the given name, these system calls fail with the error no data. If size is too small, these system calls fail with the error range. It's possible to specify size as 0, in which case the value is ignored, but the system call still returns the size of the EA value. This provides a mechanism to determine the size of the value buffer required for a subsequent call to actually retrieve the EA value. If you're heap allocating, I guess that might be useful. Note, however, that we still have no guarantee that the return size will be big enough when subsequently trying to retrieve the value. Another process may have assigned a bigger value. Yeah, it's vulnerable to races. Okay. Removing an EA. The remove xaddr, L remove xaddr, and F remove xaddr system calls remove an EA from a file. Pretty self-explanatory. The null terminated string and name identifies EA that is to be removed. An attempt to remove EA doesn't exist, fails because of no data. Retrieving the names of all EAs associated with a file. That list xaddr list. I like the syscalls. They say xaddr, which makes it very clear that it's an extended attribute, whereas the shell programs are faddr. It's like another weird inconsistency. But I prefer the syscalls naming. It seems like the kernel does a really good job at, I mean, some of them can be kind of confusing, but for the most part, they do a pretty good job at naming their syscalls like what you would expect them to be. Whereas like the user space stuff, it's just like kind of like, sometimes it makes sense, sometimes it doesn't. All right. The list of EA names is returned as a series of null terminated strings in the buffer pointed to by list. The size of the buffer must be specified in size. On success, the system call returns the number of bytes copied into list. As with get xaddr, it's possible to specify a size of 0 as 0. Excuse me. In which case, list is ignored, but the system call returns the size of the buffer that would be required for a subsequent call to actually retrieve the EA name list, assuming it remains unchanged. To retrieve a list of EA names associated with the file requires only that the file be accessible, i.e. that we have execute access to all the directories, including the path name, included in the path name. No permissions are required on the file itself. For security reasons, the EA names returned in lists may exclude attributes in which the calling process doesn't have access. For example, most file systems omit trusted attributes from the list returned by a call to list X adder in an unprivileged process. But note the may in the earlier sentence, indicating that the file system implementation is not obliged to do this. Therefore, we need to allow for a possibility that a subsequent call to getXadder using EA name returned in a list may fail because the process doesn't have the privilege required to obtain the value of that EA. A similar failure could also happen if another process deleted an attribute between the calls of listXadder and getXadder. Boom. Example program. The program in listing 16.1 retrieves and displays the names of and values of all EAs of the files listed in its command line. For example, the program uses listXadder to retrieve the names of all EAs associated with the file, and then it executes a loop calling getXadder once for each name to retrieve the corresponding value. By default, attribute values are displayed as plain text. If the -x option is applied, then the attribute values are displayed as hexadecimal strings. The following shell session log demonstrates the use of this program. So we're going to set some user attributes here, and then we're going to run their program and be able to see them. It's kind of like the dump flag. Summary: from version 2.6 onward, Linux supports extended attributes, which allow arbitrary metadata to be associated with the file in the form of name-value pairs. Exercise: write a program that can be used to create or modify a user EA for a file. The file name and EA name and value should be specified as command line arguments to the program. I'm not doing that because it's already implemented in set fheader. Alright, so that was it really quick. That was probably the fastest chapter that I've had so far. Boop, 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 boop. Let's go change this to 7. And then this is going to be access control lists. I feel like they just included this to set us up for access control lists. Get status, get at all, get DC, get CI, finish chapter 16. Get LGA. Let's do LSHLA. We're gonna do get push, and we're gonna do T7 done. %25 complete. 1/4 done. I can't wait to get halfway through this book. That'll be quite the victory. All right. Access control lists. Boom. Section 15.4 describes the traditional Unix and Linux file permission schemes. For many applications, the scheme is sufficient. However, some applications need finer control over the permissions granted to specific users and groups. To meet this requirement, many Unix systems implement an extension to the traditional Unix file permission model known as access control list ACLs. ACLs allow file permissions to be specified per user or per group from an arbitrary number of users and groups. Linux provides ACLs from kernel 2.6 onward. Support for ACLs is optional for each file system and is controlled by kernel configuration options under File Systems menu. RiserFS supports all for ACL has been available since kernel 2.6.7. In order to be able to create ACLs on an ext234 or RiserFS file system, the file system must be mounted with the mount option, ACL option. Okay. ACLs have never been formally standardized for Unix systems. An attempt was made to do this in the form of POSIX 1E and POSIX 2C draft standards, which aim to specify respectively the application program interface and the shell commands for ACLs, as well as other features such as capabilities. Ultimately, this standardization attempt foundered, and these draft standards were withdrawn. Nevertheless, many Unix implementations, including Linux, base their ACL implementations on these draft standards, usually on the final version draft 17. However, because these are there are many variations across ACL implementations, in part springing from the incompleteness of the draft standard, writing portable programs that use ACL presents some difficulties. This chapter provides a description of ACLs and a brief tutorial on their use. It also describes some of the library functions used for manipulating and retrieving ACLs. We won't go into detail on all these functions because there are so many of them. For the details, see the manual pages. Thank God. Sometimes this guy goes into way too much detail. Alright. Cool. Got a diagram, that's nice. Some source code. So this goes to page 337. We're on 321, so that's 16 pages, something like that. $18 including the one we read. Okay. Overview. An ACL is a series of ACL entries, each of which defines the file permissions for an individual user or group of users. So it's a list, a series of ACL entries. So we have tag type, tag qualifier, and permissions. Permissions I'm familiar with, read, write, execute. Group class entries. And tag qualifier. I don't understand this. Corresponds to the traditional owner user permissions. Corresponds to traditional group permissions. Corresponds to traditional other permissions. Okay. Oh, so these are the users. So you have like, okay, these are the user, like the owner of the file has these permissions, traditional owner user permissions. Then you can like specify, okay, I want these two users to have these two sets of permissions as well. But they're not the owner. They're just arbitrary users on the system, identified by their user ID. Then we have a traditional group permissions. And then here's three other groups identified by their group ID with the permissions that we want for them. And then there's some type of mask thing, which I'm not familiar with. Maybe that's a UMask. Not sure what that is. And then we have other. All right. ACL entries. Each ACL entry consists of the following parts: a tag type, which indicates whether this entry applies to a user, to a group, or to some other category of user. An optional tag qualifier, which identifies a specific user or group, user ID or group ID, and the permission set, which specifies the permissions read, write, execute that are granted by the entry. The tag type has one of the following values: ACL user object. This entry specifies the permissions granted to the file owner. Each ACL contains exactly one ACL user object entry. This entry corresponds to the traditional file owner user permissions. So this is kind of like a superset. It includes the traditional mode type permission bits. ACL user. This entry specifies the permissions granted to the user identified by the tag qualifier. An ACL may contain 0 or more ACL user entries, but at most one ACL user entry may be defined for particular users. That makes sense. ACL group object, this entry specifies permissions granted to. What if you had the bit set on the mode and then you also had an ACL? I imagine the ACL would take precedence, right? I don't know. But it seems like you have duplicate data here, or some denormalization of the model. This entry specifies permissions granted to the file group. Each ACL contains exactly one ACL group object entry. This entry corresponds to traditional file group permissions unless the ACL also contains an ACL mask entry. Curious about that one. ACL group, this entry specifies the permissions granted to the group identified by the tag qualifier. An ACL may contain 0 or more ACL group entries, but at most one ACL group entry may be defined for a particular group. ACL mask. This entry specifies the maximum permissions that may be granted by ACL user, ACL group object, ACL group, and ACL group entries, but not ACL user object. An ACL contains at most one ACL mask entry. If the ACL contains ACL user or ACL group entries, then an ACL mask entry is mandatory. So this is they say it's a mask, but it's like an allow list. I can see how there could be a mask. It depends on the binary operation you're applying to it, but in this case, it would be an or. So say I'm going to allow these bits, and that's the maximum of these bits. So then it would be an and, right? Yeah, it would be an and operation. Bitwise and. ACL other, this entry specifies the permissions that are granted to users that don't match any other ACL entry. Each ACL contains exactly one ACL other entry. This entry corresponds to the traditional file other permissions. The tag qualifier is employed only for ACL user and ACL group entries. It specifies either a user ID or group ID. Minimal and extended ACLs. A minimal ACL is one that is semantically equivalent to the traditional file permission set. It contains exactly 3 entries, one of each of the types ACL user object, ACL group object, and ACL other. An extended ACL is one that additionally contains ACL user, ACL group, and ACL mask entries. One reason for drawing a distinction between minimal ACLs and extended ACLs is that the latter provide a semantic extension to the traditional permissions model. Minimal ACLs and extended ACLs is that the latter provides a semantic extension to traditional permission. Yeah, that's what we were talking about before. Another reason concerns the Linux implementation of ACLs. ACLs are implemented as system extended attributes. The extended attribute used for maintaining a file access ACL is named system POSIX ACL access. This extended attribute is required only if the file has an extended ACL. The permissions information for a minimal ACL can be and is stored in traditional file permission bits. That makes total sense. Does that mean that if I list the ACLs for a file, it'll give me back the traditional stuff? How do you list? Get FACL. Let's do get FACL readme. Yep. That is exactly what happens. ACL permission checking algorithm. Permission checking on a file that has an ACL is performed in the same circumstances as for the traditional file permission model. Checks are performed in the following order until one of the criteria is matched. If the process is privileged, all access is granted. There is one exception to this statement, analogous to the traditional permissions model described in section 15.4.3. When executing a file, a privileged process is granted execute permission only if that permission is granted via at least one of the ACL entries on the file. That's just to prevent you from execing stuff that you don't have the intention of execing. I think it's a safety feature. If the effective user ID of the process matches the owner user ID of the file, then the process is granted permission specified in the ACL user object entry. To be strictly accurate on Linux, is the process's file system ID rather than its effective ID that are used for the checks described in this section as described in section 9.5. If the effective user ID of the process matches the tag qualifier in one of the ACL user entries, then the process is granted permission specified in the entry masked and, see, and, I was right. Oh, sorry, I'm wrong page here. Mask anded against the value of the ACL mask entry. If one of the process's group IDs, i.e. the effective group ID or the supplementary group IDs, it'd be the file system group ID, not the effective group ID, matches the file group, this corresponds to the ACL group object entry. Or the tag qualifier of any of the ACL group entries, then access is determined by checking each of the following units until a match is found. If one of the process group IDs matches the file group and the ACL group object entry grants the requested permissions, then this entry determines the access granted to the file. The granted access is restricted by masking anding against the value of the ACL mask entry if present. If one of the process group IDs matches the tag qualifier in the ACL group entry for the file and that entry grants the requested permission, then this entry determines the permissions granted. The granted access is restricted by masking anding access against the value in the ACL mask entry. Otherwise, access is denied. Otherwise, a process is granted the permission specified in the ACL other entry. We can clarify the rules relating to group IDs with some examples. Suppose we have a file whose group ID is 100, and that file is protected by the ACL shown in figure 7.1. We'll hop over there. So our user is 100. Sorry, group ID is 100. So we have some users, some groups, a mask, and other, but these are the objects. So this is going to be for 100. Okay. If a process's group ID is 100 makes a call to access file ROK, and a call will succeed. We describe access so and so. On the other hand, even though the ACL group object entry grants all permissions, I don't see that. It said what? Figure? That's table, not figure. I want figure 17.1. Where the hell is figure 17.1? Oh, over here. So our group is 100. Suppose we have a file whose group ID is 100 and the file is protected by this ACL. You have a process whose group ID is 100 makes the call access ROK. It's going to be granted that because of that permission. On the other hand, even though the ACL group object grants all permissions, the call to access ROK, WK, XOK would fail. Why would it fail? Oh, because we're also the user? No, that's not why. Because the ACL group object permissions are mask anded. I didn't know that. So we can't get X out. This entry denies execute permissions. So no one's going home with execute permissions because of the mask. Okay, this mask is a new thing. It's kind of like the UMask, but for all permissions on a file instead of for the default permission set when you create a file or directory. Okay. As another example, using figure 17.1, suppose we have a process that has a group ID of 102, and that also contains a group ID of 103. Okay, let's revisit this. As another example, suppose we have a process that has a group ID of 102, and also contains a group of 103. So that means that we would qualify for both of these two. If I could select them, doesn't want me to. For this process, the calls access ROK and access WOK would both succeed because we get ROK from here and we get WOK from here, and they're allowed by the masks. Since they would match the entries, on the other hand, call to access R or WOK, so both of them would fail because there's no matching ACL group entry that grants both read and write permissions. Interesting. So you can open up two separate file descriptors to this, one which is a read and one which is a write, but you can't open one up that is a read-write in this situation unless you're user 1010 or the owner, or yeah, that's it. Okay, let's go back over to here. Where are we? Long and short text forms for ACLs. I guess I should update the description on these things since we're talking about ACLs. Okay. When manipulating ACLs using the set FACL and get FACL commands described in a moment, or certain ACL library functions, we specify textual representations of the ACL entries. Two formats are permitted for these textual representations. Long text form. Long text form ACLs contain one ACL per line and may include comments which are started by a hash character and continue to the end of the file, end of line. The get FACL command displays ACLs in long text form. The set FACL-M ACL file option, which takes an ACL specification from a file, expects the specification to be in long text form. Short text form. ACLs consist of a sequence of ACL entries separated by commas. In both forms, each ACL entry consists of three parts separated by colons. The tag type, the tag qualifier, if there's one provided, and the permissions. The tag type is one of the values shown in the first column of table 17.1. So you can say ACL user object, so you do UGMO, that makes sense. And then whether you specify a qualifier or not is how it encodes tag type. It makes sense. Okay. The tag type may optionally be followed by a tag qualifier, which identifies a user or group either by name or numeric identifier. The tag qualifier is present only for ACL user and ACL group entries. The following are all short text form ACLs corresponding to a traditional permissions mask of 0650. So if we look at the output of get f ACL on my README, it says, where's my mouse at? User no qualifier, read write. So basically, not having qualifiers here makes these the object forms, the main forms. So these can be shortened to U, G, and O. They don't need to be typed out all the way. Just shorthand for those. The following short text form ACL includes 2 named users, a named group, and a mass entry. Okay. Oops. All right. The ACL mask entry and the ACL group class. If an ACL contains ACL user or ACL group entries, then it must contain an ACL mask entry. If the ACL doesn't contain any ACL user or ACL group entries, then the mask entry is optional. The ACL mask entry acts as an upper limit on permissions granted by ACL entries in the so-called group class. The group class is a set of all ACL users, ACL groups, and ACL group object entries in the ACL. The purpose of the ACL mask entry is to provide consistent behavior when running ACL unaware applications. As an example of why the mask entry is needed, suppose that the ACL on the file includes the following entries. So we've got a user, which has read, write, execute. We got a group, which has read and execute. We have a specific user, Paul H, that has read and execute. We have a group, teach, that has just execute. And then we have other, which has just execute. Now suppose that a program executes a following chmod on this file. Chmod path name 700. Set permissions to read, write, execute 0, 0, and 0 out of everything else. So in an ACL unaware applications means deny access to everyone except the file owner. These semantics should hold even in the presence of ACLs. In the absence of an ACL mask entry, this behavior could be implemented in various ways, but there are problems with each approach. Simply modifying the ACL group object and ACL other entries to have the mask -- would be insufficient, since the user Paul H and the group teach would still have some permissions on the file. Another possibility would be to apply the new group and other permissions settings, i.e. all permissions disabled, to all of the ACL user, ACL group object, and ACL other entries in the ACL. The problem with this approach is that the ACL unaware application would thereby inadvertently destroy file permission semantics established by ACL aware applications, since the following call, for example, would not restore the ACL user and ACL group entries of the ACL to their former states. To avoid these problems, we might consider making the ACL group object entry the limiting set for all ACL user and ACL group entries. However, this would mean that the ACL group object permissions would always need to be set to the union of all permissions allowed in all ACL user and ACL group entries. This would conflict with the use of the ACL group entry for determining the permissions according to the file group. The ACL mask entry was devised to solve these problems. It provides a mechanism that allows the traditional meaning of chmod operations to be implemented without destroying the file permission semantics established by ACL-aware applications when the ACL has an ACL mask entry. Are you studying for college? Yeah, I'm kind of retired. I just turned 41, so quite past college at this point. I'm just doing this just as a challenge, personal challenge. I've been wanting to read this book, Linux Programming Interface, for many, many years, and just haven't had the time in my career to do it. So I'm just going through it all now. And it's a lot of detail about Linux. A lot of stuff is kind of just revisiting stuff I already know from my experience, but there are a lot of details that I just wasn't familiar with, like all the ACL stuff that we're going over right now. I've never had to use this in my entire career, so the utility of it is questionable, I guess, if I've never encountered it in my career, but it would be nice to just have a better understanding of all the fundamentals of Linux, considering I'm using more Linux nowadays. So yeah, lots of cool stuff. Some of this stuff has come up in interviews in the past, like files with holes, like sparse files, has come up in a past interview. And I failed that question, of course, because at the time I didn't really have any experience with sparse files. But that's something that he has covered extensively in the beginning of the book. Sticky bits we just covered recently in the file attributes chapter, and the sticky bit came up. The semantics of sticky bit came up in an interview with Apple that I did back in 2019, and I knew of the sticky bit, but I didn't have a tight grasp on the actual semantics. It didn't prevent them from making an offer to me, but at the same time, it was one of those things in the interview that just stuck in my brain that I was like, why didn't I have an understanding of the semantics of sticky bit off the tip of my head, you know? So to answer your question, no, I'm not studying for college. It's just kind of for fun. It's for fun. It's like Nacho Libre, dude. It's for fun. All right. Where did we leave off here? I think I was. I'm like on this page. Yeah, I got a little far ahead. All right. Let's start back up on here. So the ACL mask entry was devised to solve these problems. It provides a mechanism that allows the traditional meaning of chmod operation to be implemented without destroying the file permission semantics established by ACL-aware applications. When an ACL has an ACL mask entry, all changes to traditional group permissions via chmod change the setting of the mask entry rather than the actual group object entry. A call to stat returns the mask permissions instead of the group object permissions in the group permission bit set. Oh, I didn't know that. Okay. While the ACL mask entry provides a way of preserving ACL information in the face of ACL unaware applications, the reverse is not guaranteed. The presence of ACL overrides the effect of traditional operations on file group permissions. For example, suppose that we have placed the following ACL on a file. So we have user, group, mask, other. If we then execute the command chmod group plus read write, we would then modify the mask. In this case, group still has no access on the file. One workaround for this is to modify the ACL entry group to grant all permissions. Consequently, group will then always obtain whatever permissions are granted to the mask entry. Yeah, I guess that works. The get FACL and set FACL commands. From the shell, we can use the get FACL command to view the ACL in file. umask 022 touch T file. Okay, let's go through the commands here. So UMask says when I create new files, they're going to have this mask. And this is the mask that it is ORed with, I think. Exclusive ORed, maybe. Basically, if a bit is set in, it's basically the inverse of this. If you not this, that is the mask, or that is the bits that are set on the file mode. So in this case, it'd be 755, and then we touch the file. So we can just experiment here. UMask 022, and then we touch T file, and then we ls-la. T file has 7. Not 7. 022. So that is 6. So it's read, write, execute. So it'd be 426 644. That doesn't make sense to me. Can I do UMask here? If I do Python and do octal 777, and then we just bitwise OR that, or exclusive OR that with 0022. Sorry, I have to do octal as a OX, or I think it's just O. Capital O? How do you do octal in Python? I thought 0777, I thought that was like, oh, I think it's 00777. I think they changed it. They made it so confusing. 00022, and then I want to do an XOR. That is not right. And if we do a AND, it's not right. So I have to go into this and say octal. And or bitwise XOR. There must be some other mask getting applied to it. Here, let's ask AI. Why is it with UMask 022 I get a permission set to what was it, 644? Should be removed when, so it's subtraction? No. Oh, new regular file will start with 666. So it'd be 666 like that. Yeah. So it's XORed, but your starting point is 666. Okay, that makes sense. All right. Anyways, so we have 644 now on T file, and then if we get FACL T file, it says, hey, 644. Okay. From the output of the get FACL command, we see that the new file is created with a minimal ACL, which displays the text form of this ACL. Get FACL precedes the ACL. Entries with 3 lines showing the name and ownership of the file. We can prevent these lines from being displayed by specifying the omit header option. Next, we demonstrate that the changes to the file permission using the traditional chmod command are carried through to the ACL. So we do something like chmod u is equal to rwx, and group is equal to rx, and o is equal to x, t file, and then we get our ACL, and everything looks okay. I don't care about omitting the header. The set FACL commands modifies the file ACL. Here we use the set FACL-M command to add an ACL user and an ACL group entry to the ACL. Set FACL-M user is going to be C0, and I can do RX. Group is going to be, I don't know, Docker. Is Docker even a group? Groups. Yeah, Docker. Docker can do what? X, and then we t-file get ACL. So that created a mask for us, which is equal to the group. The set FACL-M option modifies existing ACL entries or adds new entries if corresponding entries with the given tag type and qualifier do not exist. We can additionally use the option, the -R option, to recursively apply the specified ACL to all of the files in directory tree. From the output of the get FACL command, we can see that get FACL automatically creates an ACL mask entry for this ACL, which we noted before. The ACL of the ACL user and ACL group entries converts this ACL into an extended ACL. This and ls-l indicates this by appending a plus sign after the traditional file permission mask. Really? I don't see it. I see a @ sign. I don't see a plus sign. ls-la. There we go. Why does readme not have? Oh, so I think what this is saying is that @ is attributes. So if I do get f_a_attr on readme, we still have that attribute on there. So I think this @ means that there's attributes. The traditional ls just has a plus sign for ACLs that are extending the permissions, whereas the new fancy ls thing doesn't do that. But it's good to know, if you see a plus or if you see an @ then ACLs might be in play. And in the case of this new fancy, if I do type ls, this easy A thing, that it might be just attributes. It might not be extended ACLs. Anyways, where were we at? Here it is. We continue by using get set FACL to disable all permissions except execute on ACL mask, and then view the ACL once more with get FACL. Okay. Set FACL -m:\x t file. I don't know, there's some weird stuff. Get FACL on t file. Oh, cool. I like this because it says effective. Because the mask is imposing a restriction on both of these, it lists it as effective. That's super cool. The effective comments that get FACL prints after the entries for the user Paul H in the file group inform us that after masking ending against the ACL mask entry, the permissions granted by each of these entries will actually be less than those specified in the entry. Boop. We then use ls-l to once more view the traditional permission bits on the file. I wonder, is there a way that I can like get a sound notification when someone posts in chat? Let's see. Settings here. I guess that would be super annoying for anyone who has actual people in their chat on Twitch. I'll just try to keep a better eye on it. Alright. Where are we? Alright, when using the... How much more do we have on this chapter here? So 1, 2, 3, 4, 5, 6, 7, 8. Then some code and a summary. Alright, I'm going to get to 17.6 and then I need to take a bio break here. We then use ls-l to once more view the traditional permission bits of the file. We see that the displayed group class permission bits reflect the permissions of the ACL mask rather than those of the ACL group entry. The set FACL-X command can be used to retrieve entries from an ACL. Here so it uses the effective, basically. Here we remove the entries for the user Paul H and the group teach. No permissions are specified when removing entries. Note that during the above operation, set FACTL automatically adjusts the mask entry to be the union of all of the group class entries. There was just one such entry, ACL group object. If we want to prevent such adjustment, then we must specify the -n option to set FACL. Finally, we note that set FCTL-B option can be used to remove all extended entries from ACL, leaving just the minimal user group and other entries. So if I do ls-l on T file, so right now we're getting the effective for the group here instead of what the group is actually, because the mask is in effect. But if we run set FACL-B on T file, and then we ls, do we get it back? No. And if we now use get FACL on T file, it was blown away, we lost it. Okay. Alright, I'm gonna take a bio break and then we'll pick up with default ACLs on file creation here in a moment. Play some music here. Might just keep this music playing. It's nice. Alrighty. Default ACLs and file creation. In the discussion of ACLs so far, we have been describing access ACLs. As its name implies, an access ACL is used for determining the permissions that a process has when accessing the file associated with the ACL. We can create a second type of ACL on directories, a default ACL. A default ACL plays no part in determining the permissions granted when accessing the directory. Instead, its presence or absence determines the ACLs and permissions that are placed on files and subdirectories that are created in the directory. It's kind of like a UMask, but it's tied to a specific directory instead of a UMask that's applied globally to the process. A default ACL is stored as an extended attribute named extended attribute named system POSIX ACL default. To view and set the default ACL of a directory, we use the -d option of the get FACL and set FACL commands. So we're going to make dir sub, we're going to set FACL directory M. We got U, G, G, O on sub, and then we print it out. Say, hey, omit your header on sub, dump everything. Let me dial this music down a little bit more. There we go. So this is the dump, but it looks like the regular ACL. How do you know it's the default? Is the -d? I thought -d was for directory. -d is for default. So if we do set FACL help, -d is default, yeah. Okay, we can remove default ACL from the directory using the set FACL-K option to remove the default. If a directory has a default ACL, then a new subdirectory created in this directory inherits the directory's default ACL as its default ACL. In other words, the default ACL propagates down through the directory tree as new subdirectories are created. A new file or subtree created in this directory inherits the directory's default ACL as its access ACL. The ACL entry that corresponds to the traditional file permission bits are masked and against corresponding bits of the mode argument in the system call open file, open maker, and so on, used to create the file or subdirectory by corresponding ACL entries. We mean so and so. So with the default, you have a default ACL set of directory. That then gets copied on any directories. The default gets copied as the default ACL for any directories that get created inside that directory. And then any directories or files that get created inside that directory also get the default ACL applied as their access ACL applied with the mask and everything, and the mode and everything. And UMask and all that good stuff. Cool. When a directory has a default ACL, the process UMask doesn't play a part in, okay, so the UMask is ignored. Doesn't play a part in determining permissions in the entries of the access ACL of a new file created in that directory. So it's just, the default is like, takes precedence over the UMask. So it's only ANDed against the bits that are provided in the open or make dir syscall. Okay, that makes sense. As an example of how a new file inherits its access ACL from the parent directory default ACL, suppose we use the following open call to create a new file in the directory created above. So we open sub t file, we say, hey, I want to read and write to this file, create it if it doesn't exist. I want the permissions to be the owner can read, write, and execute. The group can just execute, and other can execute. So the default ACL, if I look back here, RWX is fine. So the group would just be X, and other would be nothing. Group would be read index? Why would group be? Oh, I'm sorry, I misread that. But wouldn't it just be X because we don't have read specified for group? The new file would have the following ACL: user read, write, execute. Oh, I see. The mask is ANDed with the group bits only to make it an effective mask on all of them. Okay. If a directory doesn't have a default ACL, then new subdirectories created in this directory also do not have a default ACL. The permissions of a new file or directory are set following the traditional rules. File permissions are set to the value in the mode argument given to open, make dir, and so on, less the bits that are turned off by the process umask. This results in a minimal ACL in the new file. ACL implementation limits. The various file system implementations impose limits on the number of entries in an ACL. On ext2, ext3, ext4, the total number of ACLs on a file is governed by the requirement that the bytes in all of the names and values of a file's extended attributes must be contained in a single logical disk block. Each ACL entry requires 8 bytes, so that the maximum number of ACL entries for a file is somewhat less, because of some overhead for the name of the extended attribute for the ACL, than 1/8 of a block size. Thus 496 byte block size allows for a maximum of around 500 ACL entries. Kernels before 2611 impose an arbitrary limit of 32 entries for ACLs on ext2 and 3. Other limitations I don't care about, although most of the above file systems allow large number of entries to be created in an ACL. This should be avoided for the following reasons. The maintenance of lengthy ACLs becomes a complex and potentially error-prone system administration task. The amount of time required to scan the ACL for the matching entry or matching entries in the case of group ID checks increase linearly with the number of ACL entries. Generally, we can keep the number of ACL entries on a file down to a reasonable number by defining suitable groups in the system group file and using those groups within the ACL. ACL API. The POST61E draft standard defines a large suite of functions and data structures for manipulating ACLs. Since they're so numerous, we won't attempt to describe the details of all these functions. Instead, we'll provide an overview of their usage and conclude with an example program. Programs that use the ACL API should include sysaclh. It may also be necessary to include acllib aclh if the program makes use of various Linux extensions to the POST61E draft standard. A list of the Linux extensions is provided in the ACL5 manual page. Programs using this API must be compiled with the -l ACL option in order to link against the libacl library. It's also noted on Linux, ACLs are implemented using extended attributes, and this ACL API is implemented as a set of library functions that manipulate user space data structures, and where necessary, make calls to get xadder and set xadder to retrieve and modify the on-disk system extended attribute that holds the ACL representation. It is also possible, though not recommended, for an application to use get xadder and set xadder to manipulate ACLs directly. If you're cool, that's how you do it. All right. Here's a good overview diagram, and then we got, oops, I lost the page, damn it. I need to tape that back in somehow. Let me find some tape. Maybe I can glue it back in. I don't know if I have tape. Well, I'll just stick it in here and hopefully I don't lose it. Alright. So we got a diagram, and then we got 4 pages of text, and then a program and some summary and exercises. Okay. Overview. The functions that constitute the ACL API are listed in the ACL5 man page. At first sight, this plethora of functions and data structures can seem bewildering. Figure 17.2 provides an overview of the relationship between the various data structures and includes the use of many of the ACL functions. So we got this kind of like tree looking structure here. Graph tree thing. Directed acyclic graph? No, because the cycle's going up and down. Okay. It's a graph. So we have file ACL on disk, text from form ACL, and then we have ACLT in memory ACL. ACL get file, ACL set file. ACL from text, ACL to text. I'm guessing ACL get file calls the syscall, the get x adder syscall, and then set file calls the set x adder syscall. So then we get this ACL type in memory ACL, and then we can call get ACL get entry to get the entries of it. And then we can call ACL get tag type, set tag type, get qualifier, set qualifier, get perm set to get these qualifiers, tag types, and perm sets. Repeated ACL get entry calls can be used to retrieve all ACL entries. Yeah. And then we can use ACL create entry, and it's not that bad of a API. I wouldn't say it's crazy. From figure 17.2, we can see that the ACL API considers an ACL as a hierarchical object. An ACL consists of one or more ACL entries. Each ACL entry consists of a tag type, an optional tag qualifier, and permission set. We now look briefly at the various ACL functions. In most cases, we don't describe the error returns from each function. Functions that return an integer status typically return 0 on success and -1 on error. Functions that return a handle pointer return null on error. Errors can be diagnosed using error node in the usual manner. A handle is an abstract term for some technique used to refer to an object or data structure. The representation of a handle is private to the API implementation. It may be, for example, a pointer, an array index, or a hash key. Fetching a file's ACL into memory. The ACL get file function retrieves a copy of the ACL of the file identified by path name. ACL get file path name type. This function retrieves either the access ACL or the default ACL, depending on whether type is specified as access or default. As its function result, ACL get file returns a handle of type ACLT for use with other ACL functions. Retrieving entries from an in-memory ACL. The ACL get entry function returns a handle of type ACL entry T, referring to one of the ACL entries within the in-memory ACL returned to by its ACL argument. This handle is returned in the location pointed to by the final function argument. The entry ID argument determines which entry's handle is returned. Entry ID is specified as first entry, then the handle for the first entry and the ACL is returned. Entry ID is specified as next entry, then the handle is returned for the entry following the last ACL entry that was received. Thus, we can loop through all of the entries in the ACL by specifying entry ID as first entry in the first call and specifying next entry in subsequent calls. The ACL get entry function returns 1 if it successfully fetches an ACL entry, and 0 if there are no more entries, or -1 at error. Retrieving and modifying attributes in an ACL entry. The ACL get tag type and ACL set tag type functions retrieve and modify the tag and type and ACL entry referred to by their entry arguments. I don't really need to read all this. This is like a level of detail of the C API that I don't really care to digest here. Converting an ACL between in-memory text forms, other functions in the ACL API. Example program. I'm going to skip through these because I don't do this a lot in this book, but it's just a lot of detail that I don't really need for a feature that I'll probably never use in my lifetime. I just need to know that it exists and vaguely like where to go to learn more if I need to. Alright, summary. From version 2.6 onward, Linux supports ACLs. ACLs extend the traditional Unix file permissions model, allowing file permissions to be controlled on a per user and per group basis. Further information. The final versions, draft 17, of the draft POSIX 1E and POSIX 2C standards are available online at so-and-so. The ACL manual page gives an overview of ACLs and some guidance on the portability of various ACL library functions implemented in Linux. Details of the Linux implementation of ACLs can be and extended attributes can be found in so-and-so. So-and-so maintains a website containing information about ACLs. Exercise. Write a program that displays the permissions of an ACL entry that corresponds to a particular user group. The program should take 2 command line arguments. The first argument is either the letters U or G, indicating whether the second argument identifies the user group. Function define so-and-so can be used as a second command line argument to specify numerically name. If the ACL entry for that corresponds to a given user or group falls into group class, then the program should additionally display the permissions that would apply after the ACL entry has been modified by the ACL mask entry. I mean, the getF I guess your getF ACL does this kind of, but not really, because what he wants is you to be able to say, given the user say like C0, then it would go here and it would give you back this. because it would look up and say, okay, C0. Well, C0 is the owner of the file, so it would actually get this. But if C0 is not the owner, then it would go here, and then it would be like, okay, there's a mask applied to this. I'm going to return that effective value. All right, I'm going to skip that exercise. We are just blasting through chapters today. Helps if you don't like want to do any of the exercise. All right, RMT file, we don't need that thing anymore. Vim readme, let's go here. Chapter 17 is done. We're on directories and links. All right. And then Task Warrior T7 done. We're now 26% complete. I really would like to get some tape for this page that I accidentally ripped out. Let me go look for some in the kitchen. I'll be right back. Let me jack up the music here a little bit. I found tape. Let's try and tape this page in so that I don't lose it. Alright, page is secure. All right. Directories and links. So I remember reading about directories and links from the Slackware book when I was a teenager in high school, probably. There's this thing called the Slackware book. At least I think it still exists. Pretty sure they haven't changed their website in like 40 years. Slackware book. These guys are the OGs. Slackbook, that's what they called it. Can I do maybe this? Yeah. (2012) was when they last updated it. We'll do split HTML. Most. What is most? Where more and less leave off, most picks back up. If less is more than more, most is more than less. Whereas the other pages can only display one file at a time, most is capable of viewing any number of files, as long as each file's window is at least 2 lines long. Most has a lot of options. Check the man page for full details. Most? Yeah, I don't have most. I could have sworn it was like this book that taught me like VI. Yeah, here's the VI stuff. I clearly never made it to the Emacs. I don't remember even touching Emacs. I remember learning VI and like pretty sure they used VI for everything when I read this originally. But somewhere in here they teach you about directories and how directories have entries, which are like just names that point to inodes. The directory is almost like a file that has names that point to inodes. And a file isn't actually the file name necessarily. Yeah. It's the inode of the file. That's the real thing. And that entry in a directory is just a link to the file. I remember learning that. I had to have been, it was probably 16 or 17 when I learned all that. Just starting to learn Linux. Yeah, I remember going to it was in dual enrollment. I was going to local community college. Probably junior or senior year of high school, and talking to my brother about these things. And I never thought that my career would be like so heavily dependent on this stack of technology that has just like developed and evolved over my lifetime. I mean, if you asked me back then, I would have never thought that. I mean, I wouldn't have been able to tell you what my career would have been like, but certainly had a different picture in my head when I was younger. Anyways, let's get back into reading here. It's a nice trip down memory lane here. But I'm going to blast through this because obviously I have some experience with directories and links already. Oh shit, this is a long chapter. So 372, to 340. So it's around 33 pages total. Oh no, 34. Yeah, 34 pages total, and 9 exercises. Wow. All right. Well, hopefully there's some detail in here that I've somehow managed to avoid my entire life. But if not, we'll speed read it. All right. So in this chapter, we conclude our discussion of file-related topics. Thank Jesus. I'm tired of file systems and file stuff. By looking at different directories and links. And overview of their implementation. After an overview of the implementation, we describe the system calls used to create and remove directories and links. We then look at a library function that look at library functions that allow a program to scan the contents of a single directory and walk through a directory tree. Each process has 2 directly related attributes: a root directory, which determines the point from which absolute path names are interpreted. This is the chroot, I believe, and maybe even like namespaces, I think, might be involved in. Let's ask AI. What sort of Linux namespaces are there? I think there's like a file system namespace. There's certainly a mount namespace, which deals with mount propagation. PID, network. Network was the main one. That's why it's called NewNet. User namespace, IPC namespace, PID namespace, UTC namespace, cgroup namespace, time namespace. What establishes a root directory for a container being something other than the root of the host? Oops. Is that a namespace? Or is that just chroot? The mount namespace combined with a chroot like pivot, usually pivot root. Alright, we'll investigate that later. Alright, so the root directory, which determines the point from which the absolute paths are interpreted, and a current working directory, which determines the point for which the relative path names are interpreted. We look at the system calls that allow a process to change both of these attributes. I never thought of it like that. Like the CWD, I always thought it was like this mutable thing that you can move all over the place. But I didn't really think about it like the root directory is also similar to the CWD, that you can move it anywhere with your root. You know, like you can move it other places similarly. We finished this chapter with a discussion of library functions that are used to resolve path names and to parse them into directory and file name components, directories, and hard links. A directory is stored in the file system in a similar way to a regular file. 2 things distinguish a directory from a regular file. Well, the main thing is that its file type bits are set differently. A directory is marked with a different file type in its inode entry. A directory is a file with a special organization. Essentially, it is a table consisting of file names and inode numbers. Most native Linux file systems, file names can be up to 255 characters long, which the relationship between directories and inodes is illustrated in figure 18.1 at the bottom of the page here, which shows the partial contents of the file system inode table and relative directory files that are maintained for an example file etc password. Although a process can open a directory, it can't use read to read the contents of a directory. To retrieve the contents of the directory, a process must instead use the system calls and library functions discussed later in the chapter. On some Unix implementations, it's possible to perform a read on a directory, but this is not possible. Nor can a process directly change the directory's contents with write. It can only indirectly, i.e. request the kernel to change the contents using the system calls such as open, to create a new file, link, makedir, symlink, unlink, and rmdir. All these system calls are described later in the chapter except open, which was described in section 4.3. The inode table is numbered starting at 1. Rather than 0. Interesting. Because 0 is the inode field of a directory entry that the entry is on. The inode table is numbered starting at 1 rather than 0 because 0 is the inode field of a directory entry, indicates that the entry is unused. Inode 1 is used to record bad blocks in the file system. The root directory of the file system is always stored in inode entry 2 as shown in figure 18.1 so that the kernel knows where to start when resolving a path name. Okay, so we got inode number 2, UID root, GID root, type directory, permissions, data block pointers to file data blocks, and then this is where the actual linking to other inodes. So we got temp and etc 7. So then we go to inode 7. It has its own data block pointers, and then we got password, which is 6422. We go to 6422, and then we got type file, and then it has its own data block pointers that point to the actual file data. Makes sense. I do like these diagrams. If we review the list of information stored in a file, what time is it? 3:21. I've been doing this for 2 hours. I think I got an hour left in me. All right, if we review the list of information stored in a file inode, section 14.4, we see that the inode doesn't contain a file name. It's only the mapping within the directory list that defines the name of the file. This has a useful consequence. We can create multiple names in the same or in different directories, each of which refers to the same inode. These multiple names, known as links, or sometimes as hard links, to distinguish them from symbolic links, which we discuss shortly. All native Linux and Unix file systems support hard links. However, many non-Unix file systems, e.g. Microsoft's VFAT, do not. Microsoft NTFS file system does support hard links. From the shell, we can create new hard links to an existing file using the ln command, as shown in the following shell session log. So we do an echo of some text into the file ABC. It is good to collect things. Then we ls li abc. We see it's sitting there, and then it has inode 1222232. We can then link the ABC to XYZ, and we echo, but it's better to go on blocks to the end of the file XYZ. We then cat out ABC, and it has the whole text. And if we list them out, they have the same inode number. The inode number is displayed as the first column by ls-li confirm what was already clear from the output of the cat commands. The names ABC and XYZ refer to the same inode entry and hence to the same file. In the third field displayed by ls-li, we can see the link count for the inode. After the ln abc xyz command, the link count of the inode referred to by abc has risen to 2, since there are now 2 names referring to the file. The same link count is displayed for the file xyz since it refers to the same inode. If one of these file names is removed, the other name and the file itself continue to exist. The inode entry and data blocks for the file are removed, deallocated, only when the inode link count falls to 0. That is, when all the names for the file have been removed. To summarize, the rm command removes a file name from a directory list, decrements the link count of the corresponding inode by 1, and if the link count thereby falls to 0, deallocates. So it's kind of like a reference counted garbage collector. To analogize it to memory allocation. So it deallocates the inode and the data blocks to which it refers. So when they say deallocate here in the text, like the data remains on disk. It doesn't just magically disappear because it takes work to make it zero out. So unless you securely remove it, it's going to be there on disk anyways. All of the names links for a file are equivalent. None of the names, e.g. the first, has priority over any of the others. As we saw in the above example, after the first name associated with the file was removed, the physical file continued to exist, but it was then accessible only through the other name. A question often asked in online forums is, how can I find the file name associated with the file descriptor X in my program? The short answer is that we can't. Let's think through why that is. So you got your file descriptor. It's an integer. It points at a description that then points at an inode. So technically there is a linkage to the inode, but there is potentially an unbounded amount of links that could potentially, so you'd have to walk through the entire directory structure for that partition, looking at every directory entry to find the inode. So it is possible, it's just a lot of work. So it says, he says here, the short answer is that we can't, at least not portably and unambiguously, since the file descriptor refers to an inode and multiple file names, or even as described in section 18.3, none at all may refer to this inode. On Linux, we can see which file, what you can do is create, if you have a file descriptor, you can, with the inode, you can create a new file that points to that file descriptor to keep a handle on it. You can't do that. On Linux, we can see which files a process currently has open by using readdir to scan the contents of Linux-specific proc pid fd directory, which contains symbolic links for each of the file descriptors currently opened by the process. The LSOF1 and fuser tools, which have been ported to many Unix systems, can also be useful in this regard. Hard links have two limitations, both of which can be circumvented by the use of symbolic links. Because directory entries, hard links refer to files using just an inode number. The inode numbers are unique only within the file system, and hard links must reside on the same file system as the file to which it refers. Hard link can't be made to a directory. This prevents the creation of circular links, which would confuse many system programs. Early Unix implementations permitted the super user to create hard links to directories. This was necessary because these implementations did not provide a mkdir system call. Instead, a directory was created using mknode, make node, which now is used for device creation. And then links for the dot and dot dot entries were created. Although this feature is no longer needed on modern Unix implementations, retain it for backwards compatibility. An effect similar to hard links on directories can be achieved using bind mounts. Symbolic soft links. A symbolic link, also sometimes called a soft link, is a special file type whose data is the name of another file. Figure 18.2 illustrates the situation where two hard links, home, arena this, home arena this, and home alien that, refer to the same file. And a symbolic link, home Kieran others, other, refers to the name home arena this. From the shell, symbolic links are created using the ln-s command. The ls-f command displays a trailing at character at the end of symbolic links. Let's test some things out here. One thing to note is the extended attributes are not tracked by Git. Git's like, yeah, I don't want any of that. Oh, what is this? It's just the. It's not the extended attributes, it's the change. But yeah, let's git cim finish chapter 7. I need to fix this readme. Vim readme should be 18. So we're on 18 now. Let me say finish chapter 17. Git status. All right. So what's it gonna do? Oh, echo foo into bar ln-s foo or bar baz. So baz points to bar and bar has the foo. Yeah, so this represents it instead of as an at, it represents it as a L here, as a symlink. And then if I ln instead of -s, if I ln bar to be quux as a hard link. Hard links are just regular files. If I do type on quux and type, or sorry, file on quux and file on bar, they're just ASCII text files. But if I do file on baz, it's a symbolic link to bar. If I do stat on quux or stat on bar, these are the same thing, just pointing to the same inode, but their type is a regular file. If I do stat on baz, it's like no symbolic link. So that makes sense. rm quux. Quux bar baz, or you say unlink. Echo test into bar unlink bar. Type unlink. Man unlink. I think it's the same thing as rm. Man rm is man 1. You can't rm an empty directory. It's a directory. I guess rmdr for empty directories would be like recursive use. It might do that. Alright, where did I leave off here? Oh, the add character, so that's out of date. The path name to which a symbolic link refers may be either absolute or relative. A relative symbolic link is interpreted relative to the location of the link itself. Symbolic links don't have the same status as hard links. In particular, a symbolic link is not included in the link count of the file which it refers. Thus, the link count of the inode 61 in figure 18.2 is 2, not 3. Sorry, 2, not 3. Therefore, if the file name with the symbolic link refers to is removed, the symbolic link itself continues to exist, even though it can no longer be dereferenced followed. We say that it has become a dangling link. It is even possible to create a symbolic link to a file name that doesn't exist at the time of link creation. Symbolic links were introduced by 4.2 BSD, although they were not included in POSIX 1990. They were subsequently incorporated into SUS v1 and thus into SUS v3. Boop. Representation of hard and symbolic links. So we have our inode table. We have our file data. And we have 61 and 309. So 61 is a regular file. It's pointed to by this and that. And it's just a regular file. And it just has 2 hard links to the same file. Then we have, in this directory, we have a pointer to 309 that's a type of symlink, which then points to the data for the symlink, which says home arena this, which may or may not exist. Since a symbolic link refers to a file name rather than an inode number, it can be used to link to a file in different file systems. Symbolic links also do not suffer the other limitation of hard links. We can create symbolic links to directories. Tools such as find and tar can tell the difference between hard and symbolic links. And either don't follow symbolic links by default or avoid getting trapped in circular references created using symbolic links. It is possible to change symbolic links, e.g. A is symbolic link to B, which is symbolic link to C. When a symbolic link is specified in various file-related system calls, the kernel dereferences a series of links to arrive at the final file. SUS v3 requires that an implementation allow at least POSIX sim loop max dereferences of each symbolic link component of a path name. The specified value for POSIX sim loop max is 8. However, before kernel 2618, Linux imposed a limit of 5 dereferences when following a chain of symbolic links. Starting with kernel 2618, Linux implements the SUS v3 specified minimum of the 8 dereferences. Linux also imposes a total of 40 dereferences for an entire path name. These limits are required to prevent extremely long symbolic link chains, as well as symbolic link loops from causing stack overflows in the kernel that resolve symbolic links. Some Unix file systems perform an optimization not mentioned in the main text, nor shown in figure 18.2. When the total length of a string forming a symbolic link contents is small enough to fit in a part of the inode that would normally be used for data pointers, the link string is instead stored there. It saves allocating a disk block and also speeds access to symbolic link information since it is retrieved along with the file inode. For example, exe2, 3, and 4 employ this technique to fit short symbolic strings into 6 bytes. 60 bytes normally used for data block pointers. In practice, this can be very effective optimization of the 270 symbolic links on one system checked by the author 97% where 60 bytes are smaller. Interpretation of symbolic links by system calls. Many system calls dereference follow symbolic links and thus work on the file to which the link refers. Some system calls don't dereference symbolic links, but instead operate directly on the link itself. As each system call is covered, we describe this behavior with respect to symbolic links. This behavior is also summarized in table 18.1. Ooh, nice. In a few cases where it is necessary to have similar functionality for both the file to which a symbolic link refers and for the symbolic link itself, alternative system calls are provided. One that dereferences the link and another that does not, with the latter prefixed by the letter L, for example, stat and lstat. One point generally applies symbolic links in a directory part of the path name, i.e. all the components preceding the final slash are always dereferenced. Thus, in the path name, some dir, some subdir file, some dir, some subdir will always be dereferenced if they are symbolic links. Wait a minute, I gotta reread that. Let me get some water here. One point generally applies. Symbolic links in the directory part of a path name, i.e. all the components preceding the final slash, are always dereferenced. Thus, in the path name, some dir, some subdir file, some dir and some subdir will always be dereferenced if they are symbolic links. And file may be dereferenced depending on the system call to which the path name is passed. Oh, I didn't know that. That wasn't my impression of reading the syscall documentation we read before. In section 1811, we describe a set of system calls added to Linux 2616 that extend the functionality of some of the interfaces shown in table 18.1. For some of these system calls, the behavior with respect to following symbolic links can be controlled by the flags argument of the call. That's nice. File permissions and ownership for symbolic links. The ownership and permissions of a symbolic link are ignored for most operations. Symbolic links are always created with all permissions enabled. Instead, the ownership and permissions of the file to which the link refers are used in determining whether the operation is permitted. The ownership of a symbolic link is relevant only when the link itself is being removed or renamed in a directory with the sticky permission bit set. Creating and removing hard links with link and unlink. The link and unlink system calls create and remove hard links. Link old path to new path. Here's the table, whether it follows links or not. Given the path name of an existing file, an old path, the link system call creates a new link using the path name specified new path. If new path already exists, it is not overridden. Instead, an error no exists results. On Linux, the link system call doesn't dereference symbolic links. If old path is a symbolic link, the new path is created as a new hard link to the same symbolic link file. In other words, the new path is also a symbolic link to the same file to which old path refers. This behavior doesn't conform to SUSB 3, which says that all functions that perform path name resolution should dereference symbolic links unless otherwise specified, and there is no exception specified for link. On most other Unix implementations behave in the manner specified by SUSB 3. One notable exception is Solaris, which provides the same behavior as Linux by default, but provides SUSB 3 conformant behavior if appropriate compiler options are used. The upshot of this inconsistency across implementations is that portable applications should avoid specifying a symbolic link for the old path argument. SUS-V4 recognizes the inconsistency across existing implementations and specifies that the choice of whether or not to link dereference symlinks is implementation defined. SUS-V4 also adds the specification of link at, which performs the same task as link but has a flags argument that can be used to control whether the call dereferences symbolic links. See section 1811 for further details. Unlink. The unlink system call removes a link, deletes a file name, and if that's the last link to the file, it also removes the file itself. If the link specified in path name doesn't exist, then unlink fails with the error no ent. We can't use unlink to remove a directory. That task requires rmdir or remove, which we look at in section 18.6. SUS-V3 says that if path name specifies a directory, then unlink should fail with error eperm. However, in Linux, unlink fails with error isdir. In this case, LSB explicitly permits this deviation from SUS-V3. Portable application should be prepared to handle either value of checking for this case. The unlink system call doesn't dereference symbolic links if path name is a symbolic link. If path name is a symbolic link, the link itself is removed rather than the name which it points. An open file is deleted only when all file descriptors are closed. In addition to maintaining a link count for each inode, the kernel also counts open file descriptions for the file. See figure 5.2 on page 95. If the last link to a file is removed and any processes hold open descriptors referring to my mind's wandering. Okay. If the last link of the file is removed and any process hold open file descriptors referring to the file won't actually be deleted until all the descriptors are closed. This is a useful feature because it permits us to unlink file without needing to worry about whether some process has it open. However, we can't reattach a name to an open file whose link count has fallen to 0. You can't? In addition, we can perform tricks such as creating and opening a temporary file, unlinking it immediately, and then continuing to use it within our program, relying on the fact that the file is destroyed only when we close the file descriptor, either explicitly or implicitly when the program exits. This is what the temp file function described in section 5.12 does. The program in listing 18.1 demonstrates that even when the last link to a file is removed, the file is deleted only when all open file descriptors that refer to it are closed. I thought you could do that. If a file is open by my process and all links to the files inode are, I have a FD into the files inode are unlinked. Can I relink the file somewhere so the inode isn't lost? Or what? Yeah, we'll just ask it that. Oh, that's so cool. I didn't know that. Oh, temp file. Um, man open. Sorry. Man to open. And then temp. Sorry. Temp. Sorry, I didn't copy it. O temp file. I think that's pretty cool. Okay, let's resume reading the book. Okay. So it's just a version of Unlink. The program listing 18.1 accepts two command line arguments. The first argument identifies the name of the file the program should create. The program opens this file and then immediately unlinks the file name. Although the file name disappears, the file itself continues to exist. The program then writes random blocks of data to the file. The number of these blocks is specified in the optional second command line argument of the program. At this point, the program employs the df command to display the amount of disk space used in the file system. The program then closes the file descriptor, at which point the file is removed and uses df1 once more to show that the amount of disk space in use has decreased. The following shell session demonstrates the use of the program listing in 18.1. 18.1. Boop. Listening 18.1, we use the system function to execute a shell command. We describe system in detail in section 27.6. Change the name of a file rename. Good lord. I still got a lot of reading on this chapter to do. Alright, it is almost 4. I think around 4:30 I was going to take a break. I'm going to take a quick break here right now just to check my phone because I have a thing at 6:30. I just want to make sure I got that. And if not, I'm just going to plow through here. So I'll be back in a couple minutes here. So I have probably like an hour and a half. Well, I gotta get like my chores and dinner before D&D. So yeah, let's just wrap it in a half an hour. I made some pretty good progress today. Like I'm done read ACLs, and then we start on reading what's this, directories and links. And then once we're done with directories and links, I think we still have some stuff. Yeah, monitoring file events. I think that's the last one, which is iNotify API. And then we're into signals. So we're almost done with the file stuff. So that was kind of like my goal, is to get done with the file stuff by Thursday. Because I'm just like bored with it. All right. Let's get down to business here. Changing the name of a file, rename. The rename system call can be used both to rename a file and to move it into another directory on the same file system. The old path argument is an existing path name, which is renamed to the path name given in new path. The rename call just manipulates directory entries, doesn't move file data. Renaming a file does not affect other hard links to the file. Nor does it affect any process that hold open descriptors for the file, since these descriptors refer to open file descriptions which, after the open call, have no connection with file names. The following rules apply to the use of rename. If new path already exists, it is overwritten. If new path and old path refer to the same file, then no changes are made and the call succeeds. This is rather counterintuitive, following from the previous point. We don't expect that if two file names X and Y exists, then the call rename XY would remove the name X. This is not the case if X and Y are links to the same file. Rationale for this rule, which comes from the original BSD implementation, was probably to simplify the checks that the kernel must perform in order to guarantee that calls such as rename XX, rename X ./x, and rename X some other dir X don't remove the file. The rename system call doesn't dereference symbolic links in either of its arguments. If old path is a symbolic link, then the symbolic link is renamed. If new path is a symbolic link, then it is treated as a normal path name to which old path is to be renamed. The existing new path symbolic link is removed. This is a syscall, so I don't imagine anyone ever using this directly. If old path refers to a file other than a directory, the new path can't specify the path name of a directory. The error is E is dir. To rename a file to a location inside a directory, move the file to another directory, new path must include the new file name. The following call both removes the file into a different directory and changes its name. Specifying the name of the directory and old path allows us to rename the directory. In this case, new path either must not exist or must be the name of an empty directory. If new path is an existing file or an existing non-empty directory, then an error results. If old path is a directory, then new path can't contain a directory prefix that is the same as old path. For example, we could not rename home mtk to home mtk bin. The file is referred to by old path and new path must be on the same file system. This is required because the directory itself is a list of hard links that refer to inodes in the same file system as a directory. As stated earlier, rename is merely manipulating the contents of the directory list. Attempting to rename a file into a different file system fails with the error exdev. To achieve the desired result, we must instead copy the contents of the file from one file system to another and then delete the old file. This is what move command does in this case. Working with symlinks, symlink and relink. We now look at system calls used to create symbolic links and examine their contents. The symlink system call creates a new symbolic link path to the path name specified by file path. To remove a symbolic link, we use unlink. If the path name given in link path already exists, then the call fails with error no set to exists. The path name specified in file path may be absolute or relative. The file or directory named in file path doesn't need to exist at the time of the call, even if it exists at that time. There's nothing to prevent it from being removed later. In this case, link path becomes a dangling link and attempts to dereference it. Another system calls yields an error. If we specify a symbolic link as a path name argument to open, it opens the file to which the link refers. Sometimes we would rather retrieve the contents of the link itself, that is, the path name to which it refers. The read link system call performs this task, placing a copy of the symbolic link string in the character array pointed to by buffer. The buff size argument is an integer used to tell readlink the number of bytes available in the buffer. If no error occurs, then readlink returns the number of bytes actually placed in the buffer. If the length of the link exceeds buff size, then the truncated string is placed in buffer and readlink returns the size of that string, that is buff size. Because a terminating null byte is not placed at the end of buffer, there is no way to distinguish the case where readlink returns a truncated string from that where it returns a string that exactly fills buffer. One way of checking if the latter has occurred is to reallocate a larger buffer array and call readlink again. Alternatively, we can size buffer using the path max constant described in section 11.1, which specifies the length of the longest path name that a program should have to accommodate. We demonstrate the use of readlink in listing 18.4. Susby 3 defines a new limit symlink max that is an implementation should define to indicate the maximum number of bytes that can be stored in a symbolic link. This limit is required to be at least 255 bytes. At the time of this writing, Linux doesn't define this limit. In the main text, we suggest the use of path max because that limit should be at least as large as symlink max. In Susby 2, the return type of readlink was specified as int, and many current implementations as well as older glibc versions on Linux follow that specification. Susby 3 changed the return type to size t, signed size t. Creating and removing directories, mkdir and rmdir. The mkdir system call creates a new directory. Pretty self-explanatory. The path name argument specifies the path name of the new directory. This path name may be relative or absolute. If a file with this path name already exists, then the call fails with error exists. The ownership of a new directory is set according to the rules described in section 15.3.1. The mode argument specifies the permissions for a new directory. We describe the meanings of the permission bits for directories in section 15.3.1. This bit mask value may be specified by ORing together constants from table 15.4 on page 295, but as with open, it may also be specified as an octal number. the value given in mode is ANDed against the process UMask. In addition, the set user ID bit SUID is always turned off since it has no meaning for directories. If the sticky bit is set in mode, then it will be set on the new directory. The setting of the set group ID bit is SGID, and mode is ignored. Instead, if the set group ID bit is set on the parent directory, then it will also be set on a newly created directory. In section 15.3, we noted that setting the set group ID permission bit on a directory causes new files to be created in the directory to take their group ID from the directory's group ID rather than the process's effective group ID. The mkdir system call propagates the set group ID permission bit in the manner described here so that all subdirectories under a directory will share the same behavior. SUSV3 explains, notes that the manner in which mkdir treats the set user ID and set group ID and sticky bits is implementation defined. On some Unix implementations, these 3 bits are always turned off on a new directory. The newly created directory contains 2 entries, the dot, which is linked to the directory itself, and dot dot, which is linked to the parent directory. Does that mean that those entries are actual links? Like if I do like mkdir test, and then I say, hey test, stat test, see how many links there are. There's only 1 link. But if I go under test and say I just like touch foo here, and then I mkdir test 2, and then cd into test 2, and I ls dot dot. Wait a minute, what? I hate that they broke cd test 2. Alright, and if I go back now and stat, there's still only 1 link, stat test. Okay, where did I leave off here? The dot dot stuff. So when it says which is a link to the directory itself, it's not a like link in the conventional sense, I don't think. SUSV3 doesn't require directories to contain dot and dot dot entries. It requires only that the implementation correctly interpret dot and dot dot when they appear in path names, yeah. So I think this is where the links aren't actually there. A portable application should not rely on the existence of these entries in a directory. The mkdir system call creates only the last component of path name. In other words, mkdir abc mode will succeed only if the directories a, b, or exist. This corresponds to the default operation of mkdir command. But mkdir1 also provides the -p option to create all of the intervening directory names if they don't exist. GNU library provides mkdtemp template function, which is the directory analog of the mkstmp function. It creates a uniquely named directory with read, write, execute permissions enabled for the owner and no permissions allowed for any other users. Instead of returning a file descriptor, as a result, mktemp returns a pointer to the modified string containing the actual directory name and template. SUSV3 doesn't specify this function, and it is not available in all Unix implementation since it is specified in SUSV4. RMDR system call removes a directory specified by path name, which may be an absolute or relative path name. In order for RMDR to succeed, the directory must be empty. If the final component of path name is a symbolic link, then it is not dereferenced. Instead, the error e not dir results. Remove a file or directory, remove. The remove library function, so this is a library function, not a standard, not a syscall, removes a file or an empty directory. If path name is a file, remove calls unlink. If path name is a directory, remove calls RMDR. Like unlink and RMDR, remove doesn't dereference symbolic links. If path name is a symbolic link, remove removes the link itself rather than the file to which it refers. If we want to remove a file in preparation for creating a new file with the same name, then using remove is simpler than code that checks whether a path name refers to a file directory that calls unlink or RMDR. The remove function was invented for the standard C library, which is implemented on both Unix and non-Unix systems. Most Unix systems don't support hard links. So removing files with a function named unlink would not make sense. Reading directories, opendir and readdir. I don't want to read all this. So much more. Maybe this would be good for me, reading all this. Alright, let's speed through it. Reading directories, opendir and readdir. The library functions described in this section can be used to open a directory and retrieve the names of the files it contains one by one. The library functions for reading directories is later on top of the getDents system call. I think I've used that already, and I played around with it, and it's very difficult to use. Did not have a fun time using it. Which is not part of susv3, but provide an interface that is clear to use. Linux also provides readdir system call as opposed to the readdir3 library function described here, which performs a similar task too, but is made obsolete by getDents. The opendir function opens the directory and returns a handle that can be used to refer to the directory later in later calls. The opendir function opens the directory specified by dir path and returns a pointer to the structure of type dir. This structure is so-called directory stream, which is a handle to the caller that the caller passes to other functions described below. Upon return from opendir, the directory stream is positioned at the first entry in the directory list. The fopendir function, boop. The fopendir function is like opendir, except that the directory for which a stream is to be created is specified via the open file descriptor fd. So similar to opendir, but it's called fd opendir instead of fopendir, like most things are. So many inconsistencies in the naming. The fd opendir function is provided so that the applications can avoid the kinds of race conditions described in section 18.1. After a successful call to fd opendir, the file descriptor is under the control of the system, and the program should not access it in any other way other than using the functions described in the remainder of the section. The fd opendir function is specified in susv4, but not susv3. The readdir function reads successive entries from a directory stream. So you give it the directory stream and you say, I want to read you, and it gives you back dirent. Each call to readdir reads the next directory entry from the directory stream referred to by dirp and returns a pointer to a statically allocated structure. Nice old statically allocated memory that is not thread safe. Or signal safe, for that matter. Of type dirent, containing the following information about the entry. So dirent has the inode number and the char star for the name. This structure is overwritten on each call to readdir. We have omitted various non-standard fields in the Linux dirent structure from the above definition since their use renders the application non-portable. The most interesting of these non-standard fields is dtype, which is also present on BSD derivatives, but not on other Unix implementations. This field holds a value indicating the type of the file name and dname, such as regular file, directory, symbolic link, FIFO. These names are analogous to the macros in table 15.1 on page 282. Use the information in the field. In this field saves the cost of calling lstat in order to discover the file type. Note, however, that at the time of writing, this field is fully supported only on BTRFS and the rest of the file systems that actually work on Linux. Further information about the file referenced by dname can be obtained by calling lstat or stat if a symbolic link should be dereferenced on the path name. Wait a minute. Constructed using the dir path argument that was specified to open dir, concatenated with a slash and the value returned by dname. Okay. The file names returned by readdir are not in sorted order, but rather in the order in which they happen to occur in the directory. This depends on the order in which the file system adds files to the directory and how it fills gaps in the directory list after files are removed. The command ls-f lists files in the same unsorted order that they would be retrieved by readdir. We can use a function scandir to retrieve a sorted list of files matching programmer-defined criteria. See the manual page for details, although not specified in SUSV3. Scandir is provided on most Unix implementations. SUSV4 added specification for scandir on the end of directory on end of directory or error, readdir returns null. In the latter case, setting error node to indicate the error. To distinguish these two cases, we can write the following. Error node is equal to 0, then we call readdir dir p, dir and p, and then we check to see if it's null. If it's not null, then error node is not equal to 0, then we handle the error. Else we reach the end of directory. Okay. If the contents of a directory change while a program is scanning it with readdir, the program might not see the changes. SUSV3 explicitly notes that it is unspecified whether readdir will return a file name that has been added or removed from the directory since the last call to opendir or rewinddir. All file names that have been neither added nor removed since the last such call are guaranteed to be returned. The rewinddir function moves the directory stream back to the beginning so that the next call to readdir will begin again in the first file in the directory. Rewinddir. The closedir function closes the open directory stream referenced by dir p, freeing the resources used by the stream. Two further functions, telldir and seekdir, which are also specified in SUSV3, allow random access within the directory stream. Refer to the manual pages for further information about these functions. Oh, sorry. Skipped over here. Directory streams and file descriptors. A directory stream has an associated file descriptor. dirfd function returns the file descriptor associated with the directory stream referred to by dir p. We might, for example, pass the file descriptor returned by dirp to fchangedir section 1810 in order to change the current working directory of the process to the corresponding directory. Alternatively, we might pass the file descriptor to the dirfd argument of one of the functions described in 1811. The dirfd function also appears on the BSDs, but is present on a few other implementations. It's not specified in SUSV3, but is specified in SUSV4. At this point, it's worth mentioning that opendir automatically sets the close on exec flag for the file descriptor associated with the directory stream. This ensures that open descriptor is automatically closed when an exec is performed. SUSV3 requires this behavior. We describe the close on exec flag in section 2.7. Yeah, I mean, I encountered this at my previous job where all these Ruby processes, they had a forking model where they would do a bunch of work to open file descriptors and then fork off, and they would all share those file descriptors.
when we get to socket programming, I'm curious about writing a test where I do basically that. I fork off a bunch of processes where I do the open before the fork, and then I do the open after the fork. Or I guess it'd be the connect. It wouldn't be an open, but you get the idea. I would have the file descriptor before or after, and just show the number of connections that are made and the behavior of sharing the file descriptor. Because having multiple threads write the same file descriptor of an open socket, I mean, unless they are cooperating with each other to frame their messages on different like virtual streams on the socket, the server is not going to be able to disambiguate between who sent what, and so it'll just break the connection. Because all their data will be kind of interleaved and you won't be able to untangle it. I wonder if gRPC and HTTP2 streams would solve that problem. Something to play with. I have my task warrior set up. If we do a tc none, and then we say tadd project video ideas, and we'll say ideas, create examples of pre-fork and post-fork connect IO sharing. TC, the Linux programming interface, T. Okay, clear. All right. All right, where were we? Directory streams and file descriptors. I think we read all that. Oh, it's at this point, it's worth noting that opendir automatically sets this close on exec flag for file descriptors associated with the directory stream. This ensures that the file descriptor is automatically closed when the exec is performed. susv3 requires this behavior. We describe the close on exec flag in section 27.4. Listing 18.2 uses opendir, readdir, and closedir to list the contents of each of the directories specified in its command line, or in the current working directory if no arguments are supplied. Here's an example of using this program. Okay, make sub, we touch A and B, then we list files and list them out. Not a terribly interesting program. Okay, we're getting to walking soon. The readdir function. Oh, and it's 4:30 already. All right, I guess I'll wrap there. So we're almost at walking. File tree walking, which is the next section here in 18, which is a recursive thing. And then the current working directory of a process is then talked about. And then operating relative to a directory file descriptor. Operating relative to a directory file descriptor. changing the root directory of a process. Chroot. Resolving a path name, real path, base name, their name, base name, and then summary and exercises. So not a lot. I think the biggest thing here that's going to be annoying is the walking. But I mean, most programming languages just have like very convenient ways of walking that don't involve all these like old APIs. But it'd be nice to see how it used to be done. And the rest of this is interesting and not too intense. And then monitoring file events. So tomorrow is going to be finishing up chapter 18, starting and finishing chapter 19, and then after Thursday we'll be out of the file system hell. And I'll be on chapter 20. Okay. I just get status, make sure I got everything committed, git push, and yeah, reading chapter 18. So I'm gonna bookmark it there, put that aside, and I will be on tomorrow morning. Hopefully, I think tomorrow, yeah, tomorrow I'll do a early stream where I just chill and drink some matcha and talk about what I'm going to get accomplished for the day. I started doing those yesterday, and I think that was helpful to just get me focused. I call them morning matcha and planning sessions. So yeah, I'll be on tomorrow morning, probably around, let's see, 8 in the morning my time, just to get my day started after the gym. And then I'll hop on probably around 9 to 9:30 to start reading and getting through the rest of these file system chapters. So lots of interesting stuff ahead. I'm excited for the iNotify stuff. You know, I've used iNotify before for a lot of things. It's super helpful capability, and it'd be nice to dive into some of the implementation details. So I'll be doing that tomorrow, and then once I'm done with that, then it's on to signals. And actually I'll pull up the index here. So it'd be signals for 3 chapters. So I'm excited to get into signals, but a lot of this is going to be review. This is going to be mostly review. What I'm looking forward to is like the masking stuff. Like I know I had done a few exercises around that, so I know a little bit of it, but it'd be nice to like actually do the exercises here. To understand how like the masking works. I'd like to explore more like how signal handlers and other interrupt handlers can impact your code from a correctness perspective, because it's kind of like a concurrency thing. Because like if your code is your single threaded code is executing and it's in an intermediate state, like say it's doing like some work, you know, it's in correct state A and it's doing some work to migrate to correct state B. If you interrupt the program in between doing that work, it's in an incorrect state, an invalid state, corrupt state. That can like mess up if you have signal handlers doing like interrupting your code in a way that's not compatible with your code. like a lot of these syscalls that use like statically allocated memory, if both your code and the interrupt handler are using the same code and like mutating the same static memory, like you now have like it's not actually I guess it is a concurrency issue. It's not a parallel program issue, it's a concurrency issue. Because at any time your code can be interrupted and that signal handler can run, and it could be monkeying with a lot of state that messes up your program. So I'm curious about that, like making sure that, yeah, the reentrancy stuff. Core dumps would be nice to like learn more about. But yeah, excited for what's ahead here. So this will be mostly, we'll probably get a little bit of this on Thursday, but most of it's going to be on Friday. And I'd like to wrap signals by the end of Friday. Then we're on timers and sleeping, process creation, process terminate. These are all fun things. Like I've done a lot of this already, but like mastering this stuff will be really fun. And like understanding it at a deep level, more of a deep level than I currently understand it, will be really fun. Like all these things, like they're just like topics that I just like, I'm eager to dive into. Process creation and program execution in more detail, yeah. Threads, then we get into threaded programming. I mean, I already know a lot about threads, but just like more detail, thread synchronization, like mutex. Where do you take a mutex in here? So you're creating, you're joining, you create using thread func. You take a pointer to args, which is loops, and oh, you're incrementing glob here. So you'd have to atomically increment glob here. I just want to see the system calls. Where are system calls? See, it's under pthread.h. I don't think there's a system call for mutexes. Man syscall mutex. I think it's all futex or something. Man futex. So yeah, it's in the standard library. The futex system call. Wait a minute. It is a system call. futex. So man syscalls futex. Sorry, I was on the wrong manual page. Mutex. So man2 futex. Fast user space locking. The futex system call provides a method for waiting until a certain condition becomes true. It's typically used as a blocking construct in a context of shared memory synchronization. When using futexes, the majority of the synchronization operations are performed in user space. A user space program employs the futex system call only when it is likely that the program has to block for a longer time until the condition becomes true. Other futex operations can be used to wake any process or threads waiting for a particular condition. So this is a mutex that's implemented in the kernel. uint32 is a uadder, or uint32t uadder and int op. Yeah, just like reading this whole manual page, like once you get to concurrency stuff, like he's talking about pthread API, but I want to go deeper. I want to go into like futexes. Let's see if he even talks about Futex. Yeah. Futex weight operation is in the signal handlers section too. Lots of mentions of it. So I mean, he gets into it. Anyways, let's look back here at the index. I just want to look through this. Signals, timers, process creation, termination, monitor improvement. Thread interactions, thread synchronization, thread safety and per thread storage, thread local storage, something I want to learn more about, like how it's actually implemented. Like obviously it's like somewhere on the thread stack, but the thread stacks are heap allocated, so like where is it? Threads, thread cancellation, thread further details, process groups, again something I know about just because I've encountered it, sending signals to shell processes, but all that I can like use with a good solid fundamental understanding of process priorities and scheduling. Again, I barely touched on this in my life. It'd be nice to have a better understanding. Process resources. So we are at 32 would be thread cancellation. So getting through the thread stuff would be halfway through the book. So we got a couple weeks still, I would say. This is like a long project. And I've been going hard the past couple days on this. I would say we got probably till the end of January. I'm not going to be able to finish this until February. Like the start of February. You know, if I want to take the time to actually like experiment and like learn stuff. Oh, sockets isn't until 56. I wish that was sooner. All right, we got lots of good stuff ahead of us. I kind of wanted to crank here on the past couple days to get through some of this and make some progress, because these first few chapters on all this file IO stuff is just like, I needed to get through it. Okay, tomorrow, resume on directories and links, monitoring file events, I notify, and then tapping into signals here. I'm excited for what's ahead. All right, I will see y'all tomorrow.